Hi everyone, I'm Xinhui. In this video, I'm going to introduce my final year project, Smart Object Counter. With the world's urban population drastically increasing during the past decades, the overcrowded city suggests need for effective measures in areas such as crowd control, surveillance, and dynamic traffic planning. The 2014 Shanghai Stampede is a stark reminder that inadequate crowd control could lead to disastrous consequences. The incident started on New Year's Eve, where over 300,000 people gathered for New Year's countdown. The congestion went out of control, caused 36 deaths and another 49 injured. Another use case is a microscopic cells counting. Manual inspection could be prone to human errors and produce low throughput. A robust automatic counting model could contribute to medical and biological research. This project aims to deploy density estimation-based approach on convoluted neural network, leveraging on Inception and ResNet building blocks to develop efficient, accurate, and robust deep learning model for counting tasks in highly congested scenes. The use cases are crowd counting, vehicle counting, and cells counting. This project assessed the effectiveness of Inception v4 and Inception-ResNet v1 building blocks proposed by a group of data scientists from Google. The Inception modules consists of different kernel sizes can retrieve multi-scale information, and the skip connection in the ResNet design can alleviate the gradient vanishing issue. The combination of the two allows the model to be both wider and deeper, and hence able to recognize more complex features. Proposed network number 1 and number 2 have similar structures. First of all, to leverage on the skip connection design, the network is designed to be deep for complex feature extraction. The Inception-ResNet A, B, and C modules are repeated 10, 20, and 10 times respectively for network 1. The modules are repeated for 3, 5, and 2 times for the shallower network 2. Secondly, paddings are added when necessary to control the size of feature map. The reduction blocks from the Inception-ResNet are also added to reduce the feature map to the target size. Thirdly, max pooling layers in the stem are removed. This is to ensure that the feature map is large enough and more detailed information is being passed. The average pooling and softmax layers for image classification task in the original architecture is replaced with an unsampling layer. These are the detailed diagram for the Inception-ResNet building blocks. Similar concepts are applied to network number 3, which leverages on the Inception v4 architecture. First of all, the more sophisticated stem from the original Inception v4 is implemented with minimal changes. Paddings are added when appropriate. Secondly, the Inception A, B, and C modules are repeated for 4, 7, and 3 times. Thirdly, similar to Network 1 and Network 2, the final few layers meant for classification tasks are replaced with an unsampling layer. These are the detailed diagram for the Inception v4 building blocks. The density map representation is chosen over point and bounding box annotations because it can preserve more information. It shows a spatial distribution and provides pixel-level information to be learned by the deep learning model. A Gaussian kernel G with sigma equal to 4 is used to generate the density map. Curriculum loss function is deployed during training. Curriculum learning is the notion of beginning the learning process with the easy parts and progressively move to the more difficult parts. The loss function is designed such that the model will learn from the pixels from the sparse region in each image, and then move on to the dense part. It is achieved by the dynamic threshold and the weight matrix calculated based on the image density map and the threshold. Moving on to the first use case, crowd counting. The popular dataset Shanghai Tech dataset is used. It is split into Part A and Part B, with Part A being arbitrarily scraped from the internet, and Part B being taken from the busy street of Shanghai city center. Part A is a more challenging dataset because of the higher number of count and more unstructured background. After model training, the evaluation metrics are MAE and MSE. The training result is compared with the existing works and benchmarks, it can be shown that the model produces exceptional results comparable to the state-of-the-art crowd-counting models. The trained models are also robust when being tested on images outside the given training set. Photos from Ultra Road Singapore and the NTU canteen are used to validate the model robustness. Moving on to the second use case, vehicle counting. The popular trend cost dataset is used. A mask is also provided to segment foreground and background. Sample images and the count distribution is shown here. The three proposed architectures continue to produce exceptional results. With reference to MAE, across all the test images in trend costs, on average, the model count only differs by 1 to 2 vehicles as compared to the ground truth count. The models are further tested against the images outside the dataset. The API by data.gov.sg are used to retrieve live LTA traffic photos. The model is proven to be robust for its nearly perfect count estimation. In addition, a demonstrative web application is developed using Flask to show that the model can be applied in real time. The API is called in every 60 seconds, as advised by the data.gov.sg website. The average time to process one image is 3 to 4 seconds. Moving on to the last use case, the cell counting. Malaria cell dataset is used and the model output is as follows. In conclusion, object counting in highly congested scenes is a challenging task. This project targeted on problems such as occlusion and uneven distribution, and the main contributions are summarized here. Thank you for listening.